A similar thing, do a best fit for e to the -2. Here the evidence for astrophysical flux is significantly weaker, but other than those handful of events, this is actually, it may fall into both analyses. This is really an independent look at the flux, and makes it clear that the northern and southern skies are compatible in neutrinos, and that we're seeing all of the flavors. So, so once again, it's a function of energy, the starting events, and the diffuse. So there are also that are, if this assumption is correct, this is e to the -2, and if you break that assumption and look for a best fit, you end up with something in the same order, e to the -2.3 or so, that there are, in fact, a good number of astrophysical muon neutrinos that are hiding inside the atmospheric spectrum. So these events are pretty much hidden here in a diffuse analysis, but are an inspiration to try doing a point source analysis to see if you see correlations onto the sky. So we use that to look at a point source analysis. So the point source analysis folks are at the 4-year point, and by having much looser cuts, living with sort of 90–95% neutrino purity, since you're going to put them into bins on the sky, you can allow a background to come in. So you can take more events. You end up with about 120,000 events in a 2-year period that overlaps with the diffuse analysis. So that's about 60,000 events per year. And end up with angular resolutions sort of on order of a degree at the bottom of the energy range. Down would be under right about ½ a degree at the high energy end. And that's the upward going neutrinos, 178,000 of them, as well as the downward going cosmic ray muons plotted on the sky. So now you can look for clustering in this data, and we'll just allow the red to speak for itself. As a punchline, there are no point source excesses at even low levels of significance. So nothing jumps out, but there's still something interesting you can say with the point source analysis, because you could place a limit as a function of zenith angle on the number. You can basically come up with the number of sources. Right. So in the northern sky, sensitive down to the TeV range. The southern sky, mostly to high energies, because you want to have the shower physics on the surface. If you had only one source in the sky, you would end up with a limit, a value around here. The IceCube data, at least for the upward going, is landing somewhere around 100 sources. So that's your total flux divided into 100 sources. And just put the line for where 1,000 points in the sky would be. But I think it's interesting that this is a similar number, perhaps, to the ultra high energy cosmic rays. That you end up with something on order of hundreds of sources. So hundreds of unidentified sources. That's where the limit is, not a measured value. Okay. So let me sort of work through this. So in sort of the broadest picture, we have observed astrophysical neutrinos from about 60 TeV to 3 PeV. And these are seen in a number of different analyses, all with sort of consistent picture. I think this Hesse analysis gives sort of the compelling one event at a time. Here they are, and here they are named after Muppets at the high energy end. But there's also this diffuse analysis with thousands of events, and there's been a recent effort to push the high energy starting analysis down in energy to really try picking some of those events out of the atmospheric neutrino background. Separating the cascades and the tracks, mainly from the southern sky, and then all of the tracks from the northern sky, independently, the fluxes agree, and everything is consistent with isotropic. The northern and southern skies are the same, and there are no hot spots. The pointing analysis indicates that there are no significant nearby sources. There are a small number of bright sources. Everything's consistent with a 1-to-1-to-1 flavor ratio, although this is a relatively weak statement. The IceCube design is not very good at seeing double bang tau events in this energy range. In this energy range, the two interaction points are very close to each other. So instead of bang, bang, or even two bangs near each other, you really are just elongating a almost spherical production. So that's a relatively weak statement for taus, but is a pretty strong statement for electrons and for muons. The spectrum, so in theorist-friendly terms, the spectrum could easily be fit with e to the -2 and a cutoff above a few PeV, or with a softer spectrum and no cutoff. So there's a range of possibilities there. No detection of point sources, and if the observed flux is extragalactic, then very rare sources, in particular GRBs is an excellent example. There's an analysis I didn't talk about at all that stacks up all of the GRBs that have occurred during IceCube lifetime, and puts a very, very strict limit on neutrinos from GRBs. These are constrained to a small fraction of the total flux. If there are a large number of sources, AGNs for example, or extended sources, there is no limiting on that. And galactic point sources may be within reach, and those may or may not be related to the flux. As a number of people have noted, there are a handful of events that do point to the galactic center, but it's not a statistically significant quantity. Okay. Let me just show one slide on what we've been calling Generation 2 IceCube. I mentioned Pingu, this idea of an infill, moving to lower energies, extending bringing the energy threshold down significantly to perhaps do mass hierarchy. But also hinted that the interesting astrophysics is to go high in energy, above a few hundred TeV, to perhaps only a few PeV, perhaps a narrow window. What we have is the current IceCube detector, IceCube 86 strings that are spaced at 125 meters. That was a nice conservative value at the time of the design. Basically, 125 meters is about the attenuation length, one attenuation length in the ice. However, if we would build more stations, an idea of adding another 96 strings, these might be spaced out at something closer to 240 meters, which has more than adequate signal at 100 TeV, and a layout that eliminates alleys and pathways through the detector. So the existing detector is just like the floor tiles and laid out in a grid, which has preferred axes through it. So you get large signals if you line up on larger multiplicities if you line up certain ways, and much lower multiplicities if you line up other ways. So a more organic looking layout that's it's based on log spirals eliminates those sorts of alleys. So that's an idea that's potentially doable. The shaded regions are sort of a south polism. This shaded region over here, this was red shaded region, is called a clean air sector. It's where they do rare gas measurements and dust measurements of very, very pure air that have blown about a couple thousand kilometers over the ice without any stations or anything there. So you couldn't really build anything out that way. And then this region here is dictated by the air strip and clearance for aircrafts. So, so you have to build sort of in this direction. You could also picture constructing a couple of clusters some distance away from the existing IceCube. There's actually a fair amount of merit to the edge effects in these, unlike traditional cosmic ray experiments where the edges are strictly a negative, where you want the sort of volume to them. The scale of these 100 TeV to PeV events, when you have a large enough detector, you're actually losing because the rest of the detector isn't useful to that event. So divvying it up may not be a totally crazy thing. And then the other sort of corresponding part to a Generation 2 experiment is a surface layer, surface veto. They would probably also want to try doing cosmic ray physics with. At the moment, the ice top array is just 1 square kilometer sitting directly above the in-ice part of IceCube. So it really only acts as a veto for nearly vertical events. So extending a veto out over, as it turns out, about 200 square kilometers would allow a potentially very efficient veto for even an extended detector. And these sort of sketches the detector, say this one plus 200 square kilometers of surface detector, are about an order of magnitude increase in event rate for these high energy neutrino events. Actually about a factor of 12 or so. So anyway, so this is just a few little images of where the thinking is going for what's a really early process in looking at IceCube 2.0. Anyway, that's what I had to show. So happy to take questions or have you. I'll take applause.
Okay, great. So do you think IceCube will observe glacial resonance soon, or there's some reason for not seeing it?
Yeah, I have no reason to expect events at much higher energies.
It's just a few times, right?
Yep. Everything at this point really looks as though it's either cutting off or fairly soft at high energies. So no, I don't see any expectation of large number of events out there at Glasgow.
Because you showed that there are two kind of a spectrum fit. I mean, you stay at the e to the -2 and somehow cut it somewhere, or you actually stay at the e to the -2.3. Mm-hmm. So in the second case, the spectrum will drop down, of course, sliding at the 6 dB. Would that then explain not seeing glacial resonance?
Yeah, so I don't know the numbers off the top of my head, but I think that even in the most optimistic case, unless, and there were some theory papers, right, that had some sort of dip first, I think in even the most optimistic cases, you'd be looking at an event or two out there, not tens of events. and very likely, as you run these high energy events, we're starting to fill a large part of the detector. So your energy resolution, instead of seeing a nice line, you actually may have 40% energy resolution or so for that one or two events. So I think the glass shot resonance is not going to show up as an interesting feature in IceCube data. I mean, it would be super interesting to see any events out there. But at this point, there's really the 3 events that are actually very close in energy near 2 PeV. And then there's a desert after that.
The observation of the point source compatible with the camera observation.
So if the TeV gamma ray sources are the same as the as the TeV and PeV neutrino sources, or do you mean something different?
100 TeV camera ray observation.
I don't know a simple answer to that. There's really only a handful of known sources at those sort of energies. However, those are pointed observations, so they haven't covered the sky. And if you, I think that's the short version of the answer. They are plausibly connected, and we certainly intellectually think that there's a likelihood of connection, but there certainly is not a one-to-one matching. Because we have this handful of bright, high-energy gamma sources. They are not the only point sources, but if those gamma ray sources are part of a population of gamma ray sources that we haven't fully identified, then they could be, the two populations could be the same population, right? But I think at this point, you've sampled one population very incompletely. Then with the neutrinos, you're not pointing to that subset. Does that kind of make sense? I'm not sure if my explanation was very good.
So the veto detector, that would be, I didn't understand, this would be also monitoring detectors or radio antennas?
Possibly some combination.
Okay.
So the ones we're going to deploy this coming season will actually be a plastic scintillator. But there's been sort of a number of competing. No, it's okay. There's been a number of competing ideas, and in fact, what's shown here, the little figure, is actually a small water tank. And so sort of the technology is not sort of won out in that. And depending on the staging of this, one could picture some sort of radio component beyond ARA. ARA is certainly a much shorter term project, despite the similarity in size. A Generation 2 IceCube would be 10 years out from now in construction, whereas ARA is a today construction. But you could easily imagine some radio component, either for cosmic rays or for neutrinos.
If the PV cutoff for the spectrum is confirmed, then are there any reasonable explanation, let's say from astrophysics?
That would depend on the number of sources you were seeing at 2 PeV. I don't think there's anything fundamental about that energy, about the 2 PeV energy. But if the population of sources has some inherent set of cutoffs, right, you could imagine a system that does have a particular cutoff, but I can't imagine a situation in which every one of the sources has that same cutoff. So you may be seeing just the nearest few sources then, in that case. And the cutoff need not be at all sharp, as we were saying, that you could also fit with, instead of this e to the minus 2, you could fit with a spectrum more like e to the minus 2.3 without a cutoff. The IceCube really is running out of statistics there at a few PeV.
With the source power cutoff is to be consistent with observation of the high energy protons.
I don't think I see a direct connection because there certainly are high energy protons at 10 to the 18th eV.
Okay, for the moment I suggest we make a pee break for 3 minutes, and for the faithful, you can ask whatever. I checked, we don't have a cutoff for the classroom. That's what I was worried about. So let's thank Mike again. 3 minutes.